this video, I just want to start by talking about the benefits of Kubernetes, like how it came into picture, a little bit of history. So let's jump right in. So this is how applications have been deployed over the last 2-3 decades. So initially people were just deploying applications on physical servers, and this is still the case for large enterprise databases. And sometime in the mid 2000s, VMs started getting popular. So companies started embracing VMs, and in 2013 or around that time, basically containers were introduced, and people started using containers a lot to deploy their applications. As companies started using more and more containers, they needed an orchestration mechanism to create and manage their containers. So that's when Kubernetes started getting popular, right? Because Kubernetes was developed by Google to manage Google's containers, basically for search and Gmail and all these different services. They were using a lot of containers, and they were using Kubernetes for it. So now that we know what happened when, let's actually look at some disadvantages, some reasons why technology kept evolving, starting with physical servers. So if you look at physical servers, when a company needs a physical server, they need to actually buy it, right? So they need to procure it, and it costs money. Of course everything costs money, but you need a lot of capital upfront to buy a physical server. And then once you buy it, then you need a bunch of engineers, a bunch of admins to install it in the data center. You need to keep the server cool, so that all the cooling equipments are required. So you need to spend a lot of money actually to set it up in the first place. So that's a big disadvantage. Another one is actually the amount of time it takes to actually procure, install, and get it ready for use. So it takes several months for this whole process actually. So this is very inefficient. And finally, wasted resources. So companies used to buy these big physical servers and deploy applications on them, and when the applications run, they don't even consume 10% of the CPU. So the 90% is actually sort of a cushion for this application for 1 or 2 days in a year when the application would be really busy. So all these resources were mainly wasted for most of the time. Now moving on to virtual machines. Yes, virtual machines were a great progress, definitely, because now companies do not need to buy a physical server and spend all this time to set it up. They can just partition this one physical server and create multiple virtual machine on the same physical server. But that wasn't good enough, because on this virtual machine you have to install a guest operating system, and then there is this hypervisor which is used for managing all these virtual machines. So, and these two things also consume a lot of resources, which is considered overhead. So also you have to take care of the operating system license, and you need to manage these operating systems, patch it and then keep them secure, etc, etc. So again, this was all waste of resources. So now that you understand the disadvantages of physical machines and virtual machines, you will see why containers are so important. Now containers are very small, right? They are few hundred MBs, so they can be downloaded from this registry really fast, and they can be started in a matter of few seconds. So they are really fast and lightweight. And because these things are very small and they only contain the application code and its dependencies, when the application runs, actually it's going to consume only the resources that it needs. And containers do not have their own operating system. They use the host operating system which is installed on the physical server. They kind of share that operating system. All these containers, even though they are sharing the operating system, they don't really, like, they are all isolated. Like, you know, you will, once you get into this one container, you will not see anything in a different container, and so on actually. So they are all pretty isolated. Containers are really what you need if your company is thinking about microservices, right? Because the age of monolithic huge applications deployed on this one physical server is gone. Now companies need a lot more flexibility. The applications should be more available, and you know, the all this like rollout process, everything should be very efficient, and microservice architecture or the cloud native architecture offers that to the companies. Now once a company starts using containers, very soon they're going to have like dozens or hundreds of containers running on their servers at any one point, right? So you need like a software to kind of like orchestrate these containers, like when they are created, where they are created, how many containers you need to run, which network port, etc., etc. All that is managed by Kubernetes. Now Kubernetes, again, like I said, it helps you schedule the containers, right? So let's say like a node is busy, you know, it helps a container to move to a different node, like it schedules it on a different node. When the traffic is really high, it scales out. Basically, it increases the number of replicas of a container where your application is running. It makes the deployment really, really easy. Like you can say that, okay, deploy it on this container and then route the traffic from here to here, etc., etc. So that is actually why you need Kubernetes. And even if you know, containers start crashing for some reason, Kubernetes can keep up with that. They can actually like create another container to maintain the number of replicas that you actually desire, and that you specified in this configuration file. Kube API server is one of the main components that run on Kubernetes master node. When you use a client like kubectl, it first actually starts by interacting with the API server. And not just kubectl, your API calls, Kubernetes dashboard, or any application that wants to communicate with the Kubernetes cluster, worker node components, master node components, they all first go through this API server. And this API server authenticates, authorizes, and validates those connections. When you want to deploy an application on this Kubernetes cluster, you should have some idea of the application design. For example, how many replicas of the pod where your application will be running basically should be in that configuration file. And you can also put the network details, the service details, and if you want the load balancing, you can put all that in this configuration file. And this information is basically the desired state of your application, meaning the state in which you want the application to be normally. Once this configuration file is created, it is actually sent to the API server. Now API server will basically understand the request, and then once the request is validated, it creates a pod object. It doesn't create the pod itself, it just creates a pod object, and then the scheduler will immediately come to know that there is a new pod object, and it needs to go to work to find the right node to put the pod on. So the sole purpose of scheduler is to actually find the node to create the pod. It doesn't create the pod, it just like makes that decision as in where to put the pod. And once it finds a node for this pod, it communicates that information or the decision back to the API server. From this point on, Kubelet, which is a worker node process, will take over. It will be watching this API server, and once this pod node information is available, kubelet will, or the respective kubelet will kick in, and then it will start creating the pod. And that pod is not shown in this picture. A controller is responsible for two things mainly. One is to monitor the current state of a resource or more than one resource. And if the current state of these resources are not the same as the desired state, controller will basically do things to bring it closer to the desired state. Well, you have multiple controllers in a Kubernetes cluster. So there are some built-in controllers like deployment controller, job controller, cron job controller, a node controller, a stateful set, a replica set, etc. You can actually guess like what kind of resources they control from the names of these controllers, and you can also write your own custom controllers, if none of these built-in controllers can be used for your use case. So etcd database is the primary database for Kubernetes, and it's an open source distributed key value store. So as opposed to like an RDBMS database, it's a key value store, and it's got all the cool features that all the databases nowadays offer, like high availability, strong consistency, high throughput, highly secure, reliable, etc. And etcd is one of the main components that run on the master nodes of Kubernetes, and it uses Raft algorithm for selecting its leader, because all the writes go to the leader, and in case of node crashes, like a leader node crash, then there has to be a new leader selection. For that, this Raft algorithm is used. And what does Kubernetes store in this database? It stores the configuration data, like the YAML data that we input to Kubernetes using kubectl commands. Then metadata, it's just data about data. I believe that includes like labels and annotations, and it also stores the actual and desired states of Kubernetes objects like pods. Kubelet is an agent process that basically runs on these worker nodes. As you guys know, there is two sets of nodes in Kubernetes. One is master node, where the control plane processes are. The other set of nodes are worker nodes. Kubelet basically registers, this node where it is running as the worker node with the Kube API server. It creates, destroys, or runs the pods on the worker nodes based on the pod specs that it receives mainly from Kube API server. And finally, it basically reports the health or the status of these pods and these nodes to Kube API server at regular intervals. So Minikube is basically a package or a software that lets you create a single node local Kubernetes cluster, right? So you can create a local Kubernetes cluster, and you can use it for learning and developing for Kubernetes. Of course, you will have these things mostly. These are the requirements, and mine's actually a Mac system. So having said that, actually let's start with the HyperKit installation, because that's the first thing that you need. HyperKit is basically a virtual machine manager. So I have this other link where basically they tell you how to install HyperKit using brew. So I'm going to do that first. It's pretty fast. And then let's actually install kubectl as well, because you need that. So kubectl is already installed for me. This is the version I have. And then I'm going to install the Minikube. So all brew commands basically. So as you can see, like these are showing as already downloaded. That's because of my prior installations on this laptop, and for you it might take a little bit. Okay, so all good. The installation is complete. So what else do we need to do? Okay, let's go ahead and start the Minikube cluster. But since we are using HyperKit, so we need to actually start it like this. And you can actually restrict or limit the amount of memory that your Minikube uses using this command actually. So I'm going to provide you all the documentation links, but basically if you scroll all the way down over here, you'll see a bunch of handy commands like these, and this is the command I use to actually limit the memory. So here they are limiting it to 16 gigs. I actually limited it to 8 gigs, which is why the virtual machine is being created with the 8 gig memory. Okay, all right, so it seems like the cluster has been started. So I'm going to run kubectl command. So config, so the current context is Minikube context, which is done by the installation for you. So as it shows over here, and the default namespace. Okay, now the next thing is to basically try out some Kubernetes commands in this cluster. So I'm going to actually create a deployment. I'm just going to follow this documentation, and they have like an image over here, and I'm going to expose the deployment. And what that means is actually it creates a service. So you can run this command, and that shows the service it creates. It basically creates a node port service, and this is the cluster IP, etc., etc. And one thing that you want to do is basically run this kubectl post forward. So in order to forward the port, so once you do this, what you can do is just click on this URL over here, and that actually just takes you to this web page, which is basically what that application is supposed to do. Okay, and I'm not going to create a load balancer, but what I will show you is I don't know if you can hear it. So once you start the Minikube cluster, your machine is going to be busy, and if you don't have that much CPU, that much memory, you know, on your laptop or desktop, wherever you're installing this, then it's going to be, your system's going to be slow. So you want to actually like stop the Minikube cluster whenever you are not using it. Okay, I'm going to cancel the port forwarding. I'm going to stop the Minikube cluster. And Kube Proxy is like an important component in Kubernetes architecture. Basically, Kube Proxy manages the network rules for the services actually. I am actually logged into my master node, and I also have the worker nodes over here. And first thing I want to show you is the Kube Proxy pods actually. So if you look at the pods running in Kube system namespace with this label, you will get the the pods which are which contain the Kube Proxy daemon process. So first thing I want to do is like do a deployment. first I'm going to be showing you like how many deployments I have in my Kubernetes cluster, which is 0, and then I'm going to be using a simple kubectl command to create a deployment, and I'm going to be calling it hello world, and it's an Nginx image, so it's an Nginx application with 3 replicas, and the deployment is getting created. And if I run the same command again, so there's 3 pods running, so 3 out of 3 pods are running right now. So these are the pods that are running, right? So these are having separate IPs, right, for each. Right now there is only one service. This is the default Kubernetes service. So I'm going to be using this kubectl expose command, and I'm going to be creating a hello world service on top of the deployment. So this is the port on which the service will be listening inside the cluster. Okay, so the other pods, the other applications can reach the service on port 8080. This is the port on which the application that we deployed over here, the Nginx application that we deployed inside these pods, so that is actually going to be listening on its default port 80, and then the type of service that I'm creating is the node port service. So the other one is actually a cluster IP service. So this is actually a node port service. That way we can reach this service from internet, right, from outside, not just within the cluster. So I have created a service, and if I run this command again, it shows that there is a node port service now. And if I describe this service, this hello world service that I just created, it shows the details as in like what is the IP of this service, this virtual IP, and what are the endpoints. Actually, these are the pods, and I showed you like the pods that that we created through the deployment. So if you see compare the IPs between these pod IPs and here, it will match. Since this is a node port service, we can also hit the service from internet, like I said. So let's give that a try. So the IP is my node 1, which is worker node 1 IP. Port is 3668. So when I hit that IP, I am actually able to reach the application that is running inside the pod, which is going through the service. Now let's actually see how this is happening. So Kube Proxy uses 2 different modes actually. So in one mode it uses IP tables, in the other mode it uses IPVS, so the IP virtual server. By default it uses IP tables. Okay, so the other option, IPVS, is actually useful when a cluster is running many services, like thousands of services, in which case the performance of your network is really important. Like in this case it's a simple, like my own lab, so I don't have like such fancy configuration. So now I'm just going to be running this command, this IP tables command. So let's like run this command and see like what's in the output. You can see that there is like 2 chains. They call these chains actually in IP tables, and this one is actually the one that's ending with mask is actually for the IPVS thing that I just talked about. This is the other one which is being used, actually the chain that is being used. Let's like go deeper into this. So if you look at this, you can see that there are 3 more chains actually. So I just ran this command once first, and then I ignored the first one. I used this one right here, which is for the hello world service that we created, and then I dug deeper and I got 3 more rules, and I'm taking this one, 3 more chains actually. I'm taking this one again, I'm digging deeper, and this time I get a particular IP actually. And you can see that in that first level, the port that is that we are listening on is this 3668, like we saw before, and then the packet coming into this is like traveling through this chain actually. It's going through this chain, and then finally it's reaching this IP, and this IP, if you can remember, is actually the IP of the pod. So basically these network rules were configured by Kube Proxy, actually our Kube Proxy service. So if I delete the service, let's say if I do a kubectl delete service, and the name of the service is hello world, basically all these rules will be deleted. See, all the rules are gone. So that's basically what's happening underneath. So just to summarize, Kube Proxy is a component that manages the network rules of our Kubernetes cluster, especially in this case where we are trying to use a service to reach our application, and we deployed the application using a deployment. So, and then we use this IP tables command, which I will provide in my description, to dig deeper into the IP tables configuration and how the packet travels actually like through this external port into one of these chains. Finally it reaches this IP over here, and then if I had gone into this chain, it would have showed me like a different pod. In this video, we're going to learn about Kubernetes volumes. Specifically, we're going to look at a demo to understand how Kubernetes volumes can be used to persist data over a pod lifecycle. Now on to the demo. These are the steps we're going to be performing in this demo. We'll first create a pod with no volumes, and it will run a certain command inside container as soon as the container is created, and this command will write to a log file continuously. Then we'll check the content of the log file, then we'll destroy the pod and recreate it and check the content of the log file again. And again we'll destroy the pod, and this time we'll create another pod with a volume mounted to it. Then we'll repeat the steps 2 to 5, which is checking the content of the log file, destroying the pod, and then recreating the pod and checking the content of the log file. I have already created the YAML files that we need for this demo. Let me show you this volumes_1 YAML file first. So basically the first pod that we'll be creating has the name pod with no volumes, and it will be using a CentOS image, and as soon as this container gets created, it will be running this command. And if you take a closer look at this command, it is running a while true loop, writing the date, echoing the date every 30 seconds to this log file. We'll go ahead and create this pod using the kubectl command like this. The pod is created, so let's quickly check the status of pods. As you can see, the pod is running. Now we'll check the content of the log file, which is step number 2, and we are going to run this command kubectl exec name of the container, and then we'll just print the contents of the log file. As you can see, there are 2 lines in this log file, and it was printed at 30-second intervals. Now we'll destroy this pod and we'll recreate the same pod and check the content of the log file again just to see the difference. So the pod has been deleted. Let's recreate the pod using the same command. Now the pod is being recreated. Let's check the status quickly. Then we'll again check the contents of the log file. As you can see, the log has been overwritten, or basically the previous log has been deleted forever. There is no way to go back to it. I'm going to delete this pod again. Now let's take a look at another YAML file. Now this YAML file is pretty much the same as the previous one, except it's got some extra volume related configuration. Here we are creating a volume called log directory, which is pointing to this host path, or wherever the pod gets created, the host path represents the path on that node actually, and then the actual path that this volume will be pointing to is var log, and this is a directory. So there are other options for the volume configuration like empty directory, EBS storage, NFS storage, and so on. Please refer the Kubernetes documentation for the usage of other options. Now let's go ahead and create this pod, and then this pod is going to come up with a volume mounted to it. Now the pod has been created. Let's check the content of the log file. As you can see, there are 2 lines in this log file. Now let's go ahead and destroy this pod. Now that the pod has been destroyed, let's recreate the same pod again. Now that the pod has been recreated, let's check the content of the same log file. Now as you can see, the log file still contains the data that we saw before. Like over here you can see the 2 lines that was from the previous pod, and then you can see these timestamps like 09 and 39, and you have the same lines over here. Even though we recreated the pod, these log lines or this data has been retained. In other words, the data has persisted over this pod delete and recreate lifecycle actually. Config maps are objects that help us to store non-confidential data in key value pairs in order to separate configuration from application. So let's start with basically looking at what I have on my Kubernetes cluster. I have no pods, I have no config maps, except for the default one that is created by Kubernetes during installation. I'm going to actually show you the YAML files that I'll be using to create my config map. So I have a simple YAML file like this, which is for creating a config map. I'm just defining one config map named count.org, and then in the data section I'm defining the key value pair. Basically this is actually a deployment, so it's not a pod, and the deployment basically creates two replicas, two pods. The name of the deployment is deployment CM, as in config map example. And what I'll be doing is, as soon as the containers get created in this deployment, basically it will be running a command, and it's going to consume, or it's going to use a variable called count, and the value of count is actually coming from the config map. This might seem confusing, so let's actually run some commands and it will start making more sense. So first I will be just running this kubectl apply command to create a config map. So then if I just do a kubectl get config map, you will see that this count.org config map has been created as we defined in the YAML file. So this is the count.org config map, and then if you look at if you describe that config map, you will see that kubectl describe and the name of the config map, right? If you describe it, you can see that basically this count key has the value 4 from, that's coming from the YAML file. Okay, so now I'm going to be creating the deployment, or doing a deployment, just using this kubectl apply command, and the name of the deployment YAML file is this, basically deployment with config map variables, right? So I'm going to be doing that, and if I do a kubectl get deployment, you can see that there is a deployment that's been created. Now if I just look at the pods, I will see 2 pods running because we defined 2 replicas in this YAML file. So I'm going to be using a log command to look at what this container is running currently. The log command that will be useful is this. So basically I'm going to be tailing it. I'm going to be looking at all the apps with this name. That's the label, and I want the container name, and I want the timestamps. So the commands that are running is writing to the log file, and we are tailing that log file, and it's the log is coming from 2 different pods, right? So this is one pod and this is another pod. Let's say you want to change the value of that the key that is in this YAML file. So you can go in here, and let's say I change it to 10, right? And then so basically I'm changing the value of this key count to 10 actually. If you remember the command that I showed you in my YAML file of the the deployment is this. Actually, it's basically running a for loop, and it's just doing a sequence 1 2 3 4. The value of count was 4 initially, so it was just printing 1 2 3 4, and I change it to 10 in the config map, and then I'm going to be applying this change, and then let me just make sure the change has reflected inside the config map. You can see the count value has changed to 10. Now all I need to do is a rolling restart of my deployment. So that's the command, rollout restart of my deployment, and I'm going to run this and then come back over here. You will see that the commands that are running in the container are still printing 1 2 3 4, but at some point it will stop because these containers will be blown away by the rollout. And pay attention to the timestamps actually. So now this log command basically died. Like for this pod it stopped at 1503, and then for this pod it stopped at 1503 again on this October 10. So now I'm going to run this command again, and you will see that the new log line started from 1503.06, a little bit before these containers died, these pods died. And you can see that the containers in the new pods are running this command, which is printing the numbers 1 to 10, because now it is actually running a for loop that is using the count value 10, because we have changed the config map definition. In Kubernetes, you can utilize secrets to reduce the risk of exposing sensitive data. For example, when you're creating a MySQL pod, you need to specify a root password as an environment variable. And if you don't apply the best practices to mask your passwords, you risk compromising those passwords, because it can be retrieved using simple commands quite easily. How do we keep these password-sensitive files and tokens safe then? Well, you can store them as Kubernetes secrets. Secrets can be created in 3 different ways. 1. Literal values. 2. From files. 3. YAML files. When you create secrets in one of these ways, you can try running descript commands. It won't show the password in plain text. In case of files, the location of files will not be shown in the output. While creating pods, secrets can be used as environment variables. Secrets that contain files can be mounted to pods as volumes. Then you can access those files like a regular file inside the pods. So when you're using passwords, tokens, certificates, private key files, please remember to use secrets and enhance your cluster security. So here I'm just like creating a test pod, using the Nginx image, and I am actually going to get into this pod using the kube serial execute command. And let me quickly just write something to a file in temp directory, and if you just print the content of this file, it will have the latest, whatever date that we actually redirected into that file. I'm going to exit, and then now I'm going to delete this pod, and I will be just recreating that pod. So I'm going to recreate the pod the same way and get into the pod, or you don't even have to do that. You can just directly try to print the content of this file. As you might expect, that this file doesn't exist because the pod has been destroyed or deleted and recreated. By default, it doesn't actually persist any data that is written to any file in the local file system. So now I'm gonna go ahead and delete this again because we don't need it anymore. So now actually I want to basically offer one solution for this problem, right? We want to be able to persist data because sometimes we run databases inside pods. So we want to actually persist data. That's the point, right? So let's actually just use a simple example. So this is basically like where we are using the host path option, and there is a path attribute and a type directory type attribute. So path is actually pointing to var log. That is basically the var log directory on this particular host. Actually, I'm logged into like an AWS EC2 instance. So this represents that directory. This is actually a pod YAML, right? So we are going to create a pod, and within that pod there is this one container which is going to be based on CentOS image. I'm giving some random name, and it's going to be running some command inside that inside the container once the container gets spawned. And I am going to actually mount a volume, and I'm just like, this is the name that name of the volume that I provided over here. I'm going to use the same volume name over here, and then inside the container I want basically the contents of this host directory to be mapped to this directory or this path basically. So let's actually just go ahead and create this simple pod using this YAML file, and we can use the same exec command that we used before, kubectl exec. And then this time I want to check what's in this file, right? So if I look at the content of this log file, I'm sorry, so the name of the pod is not test pod anymore. It's going to be this, which is pod with volumes. But anyway, the point is actually like, uh, once we created the pod using this command, this pod with name pod with volumes, this command ran, and then it started appending date to this file, and you can see that the date is over here, right? And then as you can see, basically whenever I created this pod before on November 8th, whatever time this is, like all these lines were written, right? So, and that data was retained. So if that's actually confusing, let's not worry about it. I'm going to actually like drop this pod, which is like the same command, delete pod, and the idea is to actually to create the pod again and just tail the log file. Okay, now the pod is deleted. I'm going to recreate it again using the apply command, and I'm going to run the exec command, which is going to tail the log file. So basically you can see that last time it was basically writing a few lines. I think it wrote a few more lines last time, and then when I ran it this time, it wrote one more line to the same log file, and the data in this log file is being retained because this is in the volume that we mounted. Well, this is actually a good solution, but this will not work in a proper company setting, like in a professional setting, because most of the times the developers will not be aware of the file systems on the Kubernetes cluster nodes actually. So what they would actually rather do is actually the topic of this video, which is like to use persistent volumes and persistent volume claims. So how do we do that? So basically you have the kind is going to be a persistent volume, and you can give any name that you want, and you will say like what is the size of this persistent volume. In this case it's 200, and then here the host path is again used, but in this case, like whenever a persistent volume is created, it is created by the cluster admin, not by the developer. So a cluster admin knows like, okay, this is the host path, and this is the path that's available on this EC2 instance, and then the access mode basically is read write once, and there is a bunch of access modes, and if you refer to Kubernetes documentation, you can find what modes are available. So basically this is the YAML file kind of like format, and I'm going to just go ahead and apply this YAML file, and it creates a persistent volume. Now the job of a developer is to first claim the space that he requires. For that, he needs to actually use another YAML file. So this is going to be persistent volume claim. That's the kind, and you can give any name you want, and how much space he needs, and also the access mode that he is interested in, the developer is interested in. At this point, like he hasn't created a pod yet, so I am actually going to go ahead and apply this YAML file. We have created the persistent volume claim. Now you can see that right away this claim was bound to this persistent volume that we had just created, and that's because the volume size was 200 MB, and then the requested size was 50 MB. So this basically Kubernetes control plane will try to find a volume that is actually closely matching with the requested size. If there are no volumes whose sizes are greater than or equal to the size requested, then basically this state will be in the status will be pending actually. But in this case we have sort of like a volume, a persistent volume that can fulfill this request, so that has been bounded to the claim. Now all the developer needs to do is basically create a pod in this way, and he's got to use a pod name, of course. It's a pod kind, he needs that, and basically the container name is my front end, etc. These are not important for us for this topic, but then the main thing is actually, like you can see that in the volumes section, the name of the volume that is given here is PV1. It doesn't have to match the persistent volume name, I've just used that. And then the persistent volume claimed is PVC1. So this is the claim name, and as long as we use this volume over here, so we're mounting this volume to this path inside the container. So I'm going to go ahead and create this pod using the same apply command. I'm just going to see what's in here. Basically it says, oh, okay, I need to replace the pod name. I always forget to do that, and it's okay to make mistakes, because nobody is perfect. Okay, so I see like an index.html file, and I want to actually see what's in there. Index.html, and then we can cat it. So this hello world. So if I do a kubectl get pod -o wide and get the IP of this my pod, because this is a nginx container, so it's going to I'm going to get the hello world HTML page, which is in this particular directory. But the point is not that, if I had to basically like destroy this pod and then recreate it again, the file will still be there. So that's basically the purpose of persistent volumes and persistent volume claims. So let's start with the smallest thing in Kubernetes, and that is a pod. And every pod has its own IP, a virtual IP, right? Which might look something like this. And each time this pod is destroyed and recreated, this IP is going to change. So the next time the IP might be 10.1.2.5. Let's say we have another pod in the same Kubernetes cluster and that wants to actually communicate with this pod. So we can use the IP, this 10.1. whatever, to talk to this pod. But what happens if the IP changes? Then we need to go here and update the IP or find some way to actually use the new IP, right? So if the IP keeps changing, it's hard to actually keep track of it and to update it here, right? Okay, and now this one is a service. Now this guy is gonna track the changes, the IP changes happening to this pod. So you can now use the IP that is associated with this service. Like this pod can just always talk to the service, and the service behind the scenes redirects the request to the pod, the correct pod, or a set of pods. So that's why we need the service. But this IP is actually like a virtual IP, right? Again, so which is not reachable from outside. What do I mean by outside? Like this pod could be running in a separate node. Let's call it node 2, and this pod, let's say, is so this pod, let's say, is running in a separate node. And each node has its own IP. But let's say there's a guy outside who wants to reach this service. He's not going to be able to use the service IP to talk to this pod, whatever port it may be. Maybe this pod is listening on port 80. The application that is running inside is listening on port 80. So what is the solution? The solution is like, or one of the solution is to use node port option. So when you create the service of this type, node port type, basically you can use the public IP of this node, which could be, I don't know, let's just make it up, 3.72.70.10. So it could be the service, the public IP of this node. And when we create a service which is going to keep track of the pod IP changes, and this service is of node port type, you can actually reach this pod through this node port service using this public IP. And what happens is this service creation randomly picks a port in a certain range, like as in 30,000 to, I guess, 32,767, something like this. And that port is allocated to this node port service. So let's just like use 30,000 for here. So now this guy is going to be able to use this IP colon this port to hit this service, right? And let's say he wants to actually reach this service, then again he needs to create, like we need to create a service on this node of node port type, and we should be able to use the public IP of this node colon whatever port is chosen randomly, right? Like 31,000, let's say. And this guy can use this public IP colon 31,000 to reach the pod over here, right? Or the service, whatever service is running over here. So as you can see, just with two different nodes, you have to keep track of the IPs of two nodes and the ports that are picked randomly, and you need to actually manage your firewall, your security group in case of AWS properly, right? So you need to open access to these ports in your security group, right? So, and it can get complicated when you have, let's say, dozens of services, dozens of nodes. It can get really complicated. Then it's hard to keep track of all these, the port, the proxy ports, and so on, right? So you can see how this node troubleshooting can get tricky when we are using this node port service, right? So one solution is actually to use a load balancer. Like let's say if you're using AWS load balancer, like a network load balancer or application load balancer, we can actually like just put all the nodes that we just talked about, like node 1, node 2, whatever. So all these can sit behind this load balancer, and we can just use the IP of this load balancer, like whatever IP that we get while creating this load balancer, and we can even choose an arbitrary port that is more familiar than one of these weird 30,000 port numbers. You can choose an arbitrary port, and this load balancer, which is provided by your cloud vendor, can take care of redirection of your request to the service that is running on one of these nodes, right? And that's based on your request, right? So this is possible. And again, like if you have multiple applications running on your Kubernetes cluster, basically, then you will have one load balancer per application in most of the cases. Then that will mean actually you'll need to create multiple load balancers, and if you want some complicated routing configuration done in load balancer, then it's gonna, like, this is gonna basically get costly or expensive, right? So that's not going to scale. It's not a bad solution, but that's not going to scale, or that's not going to work when we scale our services. Okay, so that's why you need Ingress controllers. So this is a better solution where basically you don't need to create any load balancer or anything to achieve the same thing actually, and probably more. Like once you have a proper Ingress controller installed, for example Nginx Ingress controller, then we can actually use this to do redirections just the way you want it. For example, in this Ingress resource configuration, you can say I want a particular host. Let's just call that n1.phoenix.com. So this is one of your hosts, let's say, and we can actually use the host name, and which is coming from a DNS which resolves to a particular IP. We can use this host name slash let's say, like we'll just say hello.html or home.html, whatever it is. So this is a subpath, right? So this is the main. Let's just pretend like we are running like Nginx containers behind the scenes, right? So this pod 1 or this pod is actually running like a home page. It contains the content of the home page, and let's say this pod contains the content of, let's say, order page or sell page or whatever. This whole thing is an e-commerce application, and so basically we have multiple pods serving multiple functionalities. So let's say like this host slash hello.html goes to this pod. We can actually configure our Ingress resource in that way, or we can add an additional path saying order.html, I'm sorry, slash order, let's say. Then that will probably go to this service actually, which is an order service, and that can be configured in an Ingress resource, right? Or you can even have another host name, like let's say n or node1.phoenix.com, and you can even like send or redirect your traffic basically to a different service based on this different host name, and this could be even resolving to the same IP. Okay, so that's basically why we need Ingress, and Ingress is gonna make it happen, and you will be able to use the ports which are being used by your services. You don't need any of these extra ports, and it makes our life really easy. Okay, so this is actually part 1 of my Ingress tutorial. Basically I will be creating another video which is more practical, like with a few demos. So in this video I just wanted to cover the theory part of Ingress. So hopefully you understood like why we need Ingress. Basically it's an abstraction that helps to redirect traffic properly. One of the key concepts to understand in Kubernetes is Ingress. Ingress controllers are used widely to address a routing problem that basically provides you a mechanism to define how you would like your end user traffic to be routed to a correct service. Well, in this video, I'm going to show you a demo to explain one of the advantages of using Ingress, which will help you to understand this concept a little bit more. Now, these are the requirements for the following demo. You will need a properly functioning Kubernetes cluster, and you'll also need a network plugin like Calico installed. I will put all the documentation links that you need in the description below. And now let's dive into the lesson. In Kubernetes, we have different controllers for tracking different resource types. For example, deployment controller, daemon controller, replica controller, job controller, etc. Similarly, we need a controller for managing Ingress. For this demo, we're going to be using Nginx Ingress controller. It's used quite a lot. And also, I came across this website, platform9.com, and I found the instructions to be very useful. Installing Nginx controller is really easy. It can be done using a single deployment YAML file. As you can see, it creates various resources like namespace, service accounts, cluster roles, service, jobs, etc. You can run a couple of kubectl commands to see the pods and services created by the Ingress deployment. To illustrate one of the benefits of using Ingress, I'll be creating two deployments and two services to expose the pods created by these deployments. One deployment is based on Apache HTTPD web server image, and the other one is based on Nginx image. Finally, we create an Ingress resource using a YAML file. This YAML file is where the rubber meets the road, where we actually define the rules for how this Ingress is supposed to work. Essentially, we're going to have Ingress redirect the traffic to HTTPD service or Nginx service based on the URL. Now we can go ahead and apply this YAML file. Ingress resource is successfully created now. If we look at the Ingress Nginx controller service that was created before, we can see that it is running on port 30417. Let's test this Ingress setup now. Okay, on a browser, I'm going to put the public IP of one of the worker nodes :ingress service port 30417/HTTPD. It will go to one of Apache web server pods. If I change the URL to /nginx, it will go to an Nginx pod. It seems to work. That's basically how Kubernetes Ingress works. If I had $1 for every time someone mentioned TLS in any tech company, I'd probably be able to give Mr. Jeff Bezos a run for his money. Security features like TLS are the reason why CEOs, CTOs, and founders of tech companies are able to sleep peacefully at night, knowing that their data is secure, their customers still trust them, and their stock prices are not at the risk of crashing. So how is TLS used in the context of user management / authentication in Kubernetes? Kubernetes does not have a user API object like pods or deployments. You cannot just run create command to create a user. Users are packaged into configuration context. When you initialize a Kubernetes cluster for the first time, you will automatically get a Kubernetes admin context. So if you're a new user, you need to first create a private key file, and then using that private key file, you will create a certificate signing request, CSR. CSR will contain a public key, a certificate name, and an organization name. CSR will then be signed by a CA file. This should be the same certificate authority file used by our Kube API server. This can be done using any SSL utility like OpenSSL or using kubectl. If you want to use kubectl method, then you need to create a CSR YAML file, copy the contents of the CSR created in the previous step, and apply it. Then an admin can sign the CSR by approving it. A certificate can then be created from the CSR using this command. Using the private key file and certificate, we can configure a new context and credential. You can create a new user using kubeconfig setCredentials command. Remember to use the key file and certificate file we just created. Then you can create a new context for this user. You can use the use context option to switch between different contexts. You can list all the contexts using get context option. An asterisk will indicate which context you are in currently. In a typical Kubernetes implementation, you could have a mix of individual users, groups, and service accounts, which are referred to as subjects. You can manage the access for these subjects using RBAC, role-based access control. In this RBAC method, you can create roles which will consist of various actions or verbs that one can perform on the resources like pods, deployment, etc. You can also create cluster roles which could have different privileges on some resources with a wider scope, such as nodes, persistent volumes, etc. You also need a way to associate your roles and cluster roles with your subjects, and this can be achieved by means of role binding and cluster role binding resources. So when do you use roles and role bindings, and when do you use cluster roles and cluster role bindings? If you're working with only a single namespace, then you can just use roles and role bindings. That should be able to serve most of your needs. If your need is to be able to grant the same kind of access to subjects across multiple namespaces, then you could use cluster roles and role bindings. Finally, if you want to grant some kind of access to the whole cluster, then you'll need to use cluster roles and cluster role bindings. Here's an example. I have a user called Tom who does not have the ability to view pod information in the default namespace. Let's fix this. I'm going to switch to Kubernetes admin context and create a role first. Here's the YAML file for it. In the first line, we specify the API Kubernetes provides to manage access. We specify the kind of resource we want to create. In the metadata section, you'll have things like the namespace, where the role should be created, and a name for it. Finally, we have the rules to define what type of actions we want to perform on which resources. I'm going to go ahead and apply this YAML file and go to the next step, which is to create a role binding. If you look at the role binding YAML file, apart from specifying the usual metadata information, we basically assign the role that we just created to the user who needs it. Now let's apply the role binding YAML file, switch back to the test user context, and check whether the user can view the pods that are running on this cluster. Yes, that seems to be working. If the user tries to access other resources, it should fail. And that's how you regulate access using RBAC. So let's start with actually just creating a simple pod based on BusyBox image. In fact, I'm not even going to use a YAML file to create the pod. It's a simple kubectl run command. The name of the pod is going to be BusyBox1 based on this image, and this is the command that will run after the container gets created, right? So now I am going to actually log into the pod or the container within, and let me run the ID command that shows the current user ID and the group ID and all the groups the current user is related to or associated with. So it shows that the current user is root, and of course the group is also root, and then it belongs to this group, right? So basically this is the super user. Now if I run the ps aux command, it shows all the processes running within this container, and all the processes are running as root user. Obviously, a container is actually isolated by means of namespaces, C groups, etc. If there is a misconfiguration, human error happened, these processes could get access to the resources on the host, like the host on which this container is running. The processes running inside the container could get super user access to the host resources, and if a hacker had to gain access to this Kubernetes cluster by spinning up a pod, and from that container he can do a lot of damage because he's got the super user access to these host resources. So now what can we do? Now I'm going to exit out of this pod, I'm going to show you another YAML file which is also for creating a pod based on BusyBox image. A few things are added here, so let's see. So one is actually this volume called security control volume, whatever, right? And this is the type of the volume, empty directory. And you have all these, you have one container and we are mounting this volume to this container. And of course we are running sleep 3600 after the container gets created. And this part is very important. This is where we are adding the security context that I was talking about. Now the first thing I'm saying is any container that is created within this pod should have these specs, right? So those processes should run as user 1000, and the primary group of those processes should be 3000, and this FS group is another secondary group or additional group that I am specifying. This volume will be owned by this group. Any file created under this volume will be owned by this group. Okay, so let's actually see all those things in action. So I'm going to go ahead and create this BusyBox2 pod. So I'm going to be using the same exec command to log into this one of these containers. If I do ID, you will see that it's going to be user ID 1000 and group ID 3000, and additional group is also there actually. So 1000, 3000 and 2000. So that's exactly what we wanted. If I do a ps minus a ps aux just to see the processes, all the processes are running as the user 1000. And if I do ls minus ld, what's the name of the volume that we mounted? This is the name of the volume that we mounted to this path, and you can see that it is owned by root, but the group owner is 2000, and that's because we have specified in the security context spec over here that it should be 2000. Now if I create some dummy file like here, right? So first of all, it says permission denied. So let's actually go into data demo and try to create the file over there. This is awesome. So we are able to create the file here. Now look at the owner of the file, that is 1000, that's the current user, that's okay, and the group owner is 2000, right? So that's, you know, that's what we exactly wanted. Now another detail that we want to understand is, now if you see this YAML file, the spec is basically for this whole pod, right? Now I can move this spec to a particular container, right? So if this is under pod spec, then the security context settings will be applied to all the containers that are part of this pod. If I move it to a specific container or multiple containers, only those containers will have this security context, right? So basically you can put the security context under pod or certain containers. Now if you put the security context in both pod spec and container spec, basically the container specs are going to override the pod spec settings. So let's actually do this, so I have another YAML file called node.js, and I am creating another pod based on a node.js image. So this is node:/slim. It's a slim image and it's a node.js image, and I'm specifying this security context called run as user 1000, right? So now let me go ahead and create this pod. And I will go ahead and log in the same way. Now here is the surprise. If I run id command, you will see that it is running as 1000, user 1000, 1000, but you can see the user name, and that's because like some containers or some images come with pre-created users, right? So if you look at this password file, you will see that there is a user called node which has the user id 1000 pre-created, whereas before when we ran the id command in busybox2 container, we just had 1000, 3000 and 2000 because these were not pre-created. So you have many applications running in your Kubernetes cluster, right? So you have these applications are running in pods, and these pods are getting incoming traffic or ingress traffic, or they're also communicating to other pods actually. So that's outgoing traffic or egress traffic. So, and you want to actually have some control over like which pods can talk to which pods, or which applications can talk to which applications, and vice versa, right? So for that actually you can use network policies. So network policies is basically an API that Kubernetes offers, and like coming out of the box, actually the features that Kubernetes network policy API offers is limited. It's basic, and if you want more features, then you can go to other CNI plugins like Calico. We'll talk about that later. First, actually, let's just look into this common use case. You have like different applications running in your in your Kubernetes cluster. So you could have databases, you could have backend code like Python, Java code, and you could have like front-end code. Generally, backend applications are the ones which talk to database pod, and you don't want your front-end applications to be talking to your database. So you want to actually block the traffic coming from your front-end pod. Okay, another use case is you have multiple types of environments. Actually, you have production environment, you have staging, you have QA, dev, all these environments. And generally, you don't want the traffic from your non-prod environments to be like talking to your prod environment, right? So for those kinds of like traffic control, right? So you want to block some traffic from actually reaching to a certain destination. For that, you basically use the network policies. So, and how do you actually identify this traffic? You can actually identify pods. You can say that I don't want, or I want actually to block a certain IP range, or you can say like I want traffic from this namespace to be allowed, and so on. And you can do that by means of using labels. So now that's the theory part. Let's jump to a quick demo and understand how it actually works. So you have like multiple pods actually. So I created like a database pod, and I created a couple of application pods actually, or backend pods. So one is called a Python dev, and another one is called Python prod. One is a dev environment, let's assume. Another one is a prod environment. So the idea is actually like if I connect to let's say my dev environment, and I'm actually going to use a simple MySQL program or a script a Python script to basically try and connect to the database. And shockingly, actually, we are able to connect it from dev, and we can do the same from prod, and that's okay, right? So I'm going to quickly show that to you. So if I just do Python temp, and we are able to connect to the database, the MySQL database, right? And that's possible from both the pods. So the idea is actually to block the traffic, the ingress traffic coming from this dev pod actually, right? So for that we need to implement a network policy. So the network policy is this np.yaml. So you have the kind network policy, and it's coming from this networking API, and I'm going to name it MySQL network policy. It's in the default namespace, and I'm providing the specs for the rules, right? So you have, okay, this is actually being applied on MySQL pod. So the label, if you look at the labels of these pods, which I should show you. So let's go ahead and look at the labels. Describe pod MySQL. I'll just do more. We don't need to see all of it. For MySQL, you have this label which comes by default, and let's look at the label for Python dev. And that one has this label env equals dev and Python prod. So the label is env equals prod, right? So these are different labels that we have for our applications. So here I'm selecting this label run :MySQL, and so this network policy is going to be applied on this MySQL pod, or for this MySQL pod. Okay, what kind of traffic do I want to control? Ingress. Okay, and I'm just going to say that any environment which has this label, which matches this label, environment prod, is actually allowed to connect to this MySQL pod, right? So that's basically a very simple rule, right? So we're going to see this simple example in action. I'm going to go ahead and apply this policy. Okay, the policy is created. So now let's try to actually connect to my dev pod. Let's see, up the pod, say dev pod right here, and I'm going to try and run that the same MySQL script which connects to the database and gets that information. And that was possible before, right? Because if you remember, we connected to Python dev, or attached to Python dev, and then we ran the program and it worked. And now it's hanging. So that means actually the network policy is actually blocking the traffic going from here to the database pod. Now we don't want the same to be happening for our prod pod, right? That's a tongue twister. So let's actually go ahead and run this one, which is working actually. So that's what we want. So we have successfully blocked the connection coming from our dev pod actually. So that's basically the point. That's how you use network policies. That's basically it. We know that like when we create pods, there are containers running inside them, right? So those are the ones that I'm calling app containers. They are normal containers. And you can also have like what they call init containers. So init containers are meant for a specific purpose. You can have multiple init containers, just like how you can have multiple app containers. So let's see like why you need them, what they are, and things like that. So first of all, init containers, as you might have guessed, they actually run first. When a pod is created, they run first, and then they run to completion before uh, before actually the application containers are started, right? So they run to completion. That's very important. Now, if the init containers crash for some reason, it will never move to the next stage. Either the init containers will keep on restarting. There are many ways to work with it, but basically, in most cases, the init containers will keep restarting and running the scripts or commands that are meant to be run inside the init containers. And then only after they finish, it will let the application container to start, right? So that's the main thing to understand. Now, what are some use cases, right? So the first one is a delay. Like if you want to have some sort of delay before your actual application comes up, like 5-minute delay, 10-minute delay, or even just 1-minute delay, you can put the wait command in your init container and just let the init container come up and the wait will happen, and then it will move to creating your application containers. Or you can wait for other services to come up, like like in case of backend applications like Java, Python. Those backend applications can wait for the database to be available before the application is started, right? So that's waiting for other services. That can happen inside init containers. Now, one other use case that I'm aware of is basically in cases where you need to have like better privileges, like privileged user access to change, like say the ownership of a file system or just a permission of a file, or or you probably need to access Vault for some reason and you need access to secrets. All those like high uh, privilege actions can be part of init containers. But basically those things that need to happen that require higher privilege, they can be part of init containers before the application is started, right? So now to explain how I'm going to be doing a demo, of course. So we're going to basically have a simple uh, database. So there's a init container that's going to wait for the database to be available before the main application, I'm going to call it my application, is started. Okay, so let's jump to the demo. Now, I don't have any pods running. So the application that I'm going to be creating is my application, right? So that's the pod that I'll be creating. And inside that pod, if you try to just understand this part, so you have the container section, which is actually the main application, and I just kept it simple. I'm using a popular image called BusyBox. So that let's just assume that that is the main application, right? So that's the main container that we want to run. But before that, actually, there is a init container section. And in the init container, I'm going to be running a simple command actually. And or a bunch of commands. And what that command does is it is going to basically run a Python program. And the Python program will actually connect to the MySQL database. And if the database is not available, it's going to keep trying until the database is available. And once the database is available, then the init container will finish. It will run to completion. Then the application container will be created. And you don't have to worry about the volumes and volume mounts and all that. It's just a method I am using to just stage this program inside the init container, right? So I will share this manifest with you, this YAML file with you, like in case you want to practice in your Kubernetes cluster. So now let's keep going. So I'm going to go ahead and create this application, right, or pod. So all right, so let's see actually what's happening inside. kubectl get pods. So as you can see, you have your pod that is trying to come up, my application, and it's actually in the init state, meaning like it's like running the init container. And what is it doing exactly, right? If you are curious about that, you can run like a log command or a command to just fetch the logs. You can see that initially it probably ran like uh, the pip commands to download the MySQL connector package and so on. And it's like, it seems like it's like waiting for something, right? Because as you can see, the init is still running. It's been like about 50 seconds. And as you know, like that it is actually waiting for the database to be available, database service to be available, right? So now I am actually gonna go ahead and just spin up a database, right? So this will be the database pod. So if I do a get pods now the MySQL pod is actually running. Okay, here's the log command that I ran actually to tail the log of the init container, which is init database. And initially, actually, the database was not available, so it was waiting for the DB initialization. Then as soon as it figured out the database is available and it is able to connect to the database, it exited the init container. Now our application is running. So first of all, what is a liveness probe? So the answer is in the question. So it basically is a way to check or probe and find out whether the container running inside your pod is healthy or not. So let me say that again. It's basically a way to check, to health check your container, the container running in your pod. Okay, so we're going to actually understand that further by using this example straight from the documentation. So I just copied that code, the YAML, into my Kubernetes cluster. I am on the master node and a couple of worker nodes. We don't need to worry about that. So here's the example that they've given. So let's try to understand this. So this is actually a pod creation YAML file, right, with the V1 API version. And there's some metadata. We're naming this liveness exec, and there's a label. These are not that important, at least for this purpose. And we have a spec. And what's in the spec? So we have a spec for the container that's going to run inside the pod, and the container is going to be based on this busybox image, and there's a certain argument that is passed for when the container starts. This command is going to kick in, right? So what is this command? This command just creates a file, then it sleeps for 30 seconds, then it removes a file, then it's going to sleep for 600 seconds. That's what's going to happen as soon as the container starts. There is a section that comes under containers as well, and that is called liveness probe. And what is this liveness probe going to do? So this is going to execute this command based on which the health of the pod is going to be determined. So this command is going to run cat temp healthy. And this is the same file as the one that is created by this command. So if the file is present in this container, so this command is going to come back with a success exit code, right? 0. Okay. If this file is not present after this remove command, it is going to be removed, right? So if this file is not present, then this command is going to come back with some error code actually, right? So based on this command, we're going to see if the container is healthy, or we're not going to do anything. Basically, the liveness probe is going to take care of it. Now, what is this initial delay seconds? It's just telling the liveness probe to start after 5 seconds, right? Not immediately. Like if it's done immediately, then this file is probably not going to be available, so that might cause some issues. So we're going to say delay for 5 seconds before you start checking the container, and then period seconds. That's actually the interval between the checks. So it's not just going to happen once, it's going to happen continuously, and every 5 seconds we're going to check this check by running this command. Okay, sounds good. So let's go ahead and do a cleanup first. I want to make sure there's no pre-existing parts. So let's actually delete these pods that I've created before. We want like a clean slate. Okay, so those are cleaned up. So now I'm just going to create this pod. So let's check on this pod. So right now that pod is up and running, right? And let's in fact get more details about this pod by running the describe command. Okay, now you can see what's happening. We're basically placing the pod on node 2, or the worker node 2, and we're pulling the busybox image, we're creating the container, etc. So at this point, there's nothing fancy going on. It's just a normal pod that is running. So let's run this again, and now you see something interesting. Now it says the liveness probe failed because it cannot open this particular file. Remember, we are trying to run a cat command to do this check, so we're not able to open this file. So now this file is going to basically the liveness probe is going to destroy this container and it's going to recreate it. Okay, so if you run this again, you will see that it's created the container again. Just created the container, and that's what liveness probe does. It basically checks the health of the container, and if it's not healthy, it's going to drop the container or delete the container. It's going to create it again from the image that we defined in the YAML file. Now another version of liveness probe, which is probably more useful, is this one. Which is basically very similar, but this time we're going to be using an Nginx container, and what we're going to do is probe on a particular URL, right, on basically port 80, right? So this is Nginx, right? So we know that Nginx has a default page, web page. So if you let me create the container first. Okay, so we have the container. So if I do a kubectl get pod, and I want to get the IP this time, so let me get the wide output, and this one is the IP. So if I do a curl and that IP, then we get the default web page, right? So this is the default web page coming from index.html. So now the liveness probe is happening, and what it is doing is it's basically going to this index.html and grabbing the web page, right? So now Liveness Probe is not just running a command, it's actually trying to reach a particular URL and exactly this path and exactly this port. And these two are pretty much the same. The initial delay second is 3 seconds, and then the checks are happening every 3 seconds. So this, as you can see, could be a little more useful, right? Because we want to be doing things like this. We might be running a web server. We want to check on the health of the web server by trying to get to a particular URL, a particular path on a particular port, right? So if I go inside this container and delete this guy, which let me do. So I'm going to go inside this container. Okay, let me go ahead and run this command. I want to do this, and I want to get into nginx container. I want to have a bin bash shell actually. Okay, so what I'm going to do is I'm going to find this index.html, which should be inside this user, and I'm going to be just renaming this file, you know. So I'm just going to call it whatever, and if I exit now and let's say I do this, it's still running. So let me actually do a describe on this guy. As you can see, again our Liveness probe failed with the status code 404, right? If I do a curl again, it comes back because our Liveness probe has already recreated the container. So let's actually take a quick look at my cluster. So I've got like one master node and 2 worker nodes. All right, so let's take a look at the Cordon command first. I'm going to Cordon node 2, and then if I quickly run this command, you will see that node 2 is basically having this scheduling disabled status, right? If I just create a pod or a deployment or any resource, basically, like in this case I'm creating a pod quickly, and if I ran kubectl get pods and void output, you will see that that pod basically was scheduled on node 1, and no matter what resource is created, it will basically not be scheduled on node 2 because we have cordoned node 2. You can cordon a node and you can just wait for the applications to, like, you know, do their deployments. You can actually wait for them to go away from your node. That way you can do some sort of maintenance activity like a restart or an upgrade, or like, yeah, so you can do any maintenance activity on that particular node. So cordoning a node does not actually disturb the existing pods. Like in this case we cordoned node 2, but as you can see, the pods that are running on node 2 are still running. Actually, we haven't like kicked them off. So unless someone does a deployment, you know, a rolling restart, something like that, these pods will continue to run on this node actually. So this will not disturb the existing pods. Okay, so we have that. So I'm going to go ahead and delete the pod I just created, and I'm going to go ahead and undo the cordon operation that I did. So now our cluster is sort of back to the normal state. So all the nodes are good. scheduling is not disabled anywhere. So now I'm going to create another deployment called test deploy, and that's going to have 5 replicas, and it's based on busybox image. Let's actually take a look at how our cluster looks, because you never know. So we have 5 pods which are created by the deployment, and most of them are running on node 1, but this one is running on node 2. Okay, so let's say that I want to actually do some maintenance on node 1, and this time I just don't want to cordon and wait for the pods to clear out. I want to actually like be a little more aggressive and then kick off the pods on node 1. So in this case, I'm going to run this command called drain. So and then it says draining is fine, but then there are some pods which are in the Kube system namespace, and these are daemon sets. So it says like I cannot delete these kinds of pods. So if you want to ignore them, just go ahead and ignore it using this flag. So as you can see, as soon as I run this drain command, it is basically evicting the pods that are running on node 1. So it basically clears out that node, and if I run this command, you will see that basically everything will be running on node 2, right? There's nothing running on node 1. So now node 1 is free for whatever maintenance you want to do. Okay, so if you do a kubectl get nodes, you will see that this node 1 is also having the scheduling disabled. A drain command not only evicts the pods, it starts by like cordoning the node itself. So what are service accounts and why do you need them? Now think of a scenario where you need to actually interact with your Kubernetes resources like pods, nodes, deployments, replica sets, whatnot, from inside a Kubernetes pod, right? You might have to do that when you're setting up your CI/CD pipeline, and the pipeline might create a pod which manages your deployments, right? Your application deployments. Or you might have a pod which manages the node maintenance operations in your cluster. So here I have a command kubectl get SA. SA stands for service accounts, and there's a couple of accounts in my cluster. This default account comes as part of the installation. So this my SA account is the one that I created a couple of days ago, and you will also see that for this default account, there's a default token which is stored as a secret in the Kubernetes cluster, and there's a MySA token which is stored as a secret in the same Kubernetes cluster. So these are automatically created when you create a service account. So let's go ahead and create a simple service account. So I'm going to call it new SA account. Okay, so if I run this command again, you will see that I have this new service account. And if I run this command to get or the list the secrets, you will get new SA token, some alphanumeric character, right? So this was automatically created. So I'm going to create a pod, and I want this pod to be able to authenticate with the Kubernetes APIs, and I want to run some commands inside the pod to list the pods that are running inside this cluster. So what pods do we have inside this cluster? We have a couple of deployments or pods that came from deployment. So, and that's it, right? And if you look at my pod YAML, this YAML file, it looks like any other YAML file, nothing fancy, but you have this based on Nginx image, and I'm going to call it test pod actually. Then the only thing that's different is the service account that I want to associate with this pod. Okay, so basically this service account will be associated with this pod, and I'll tell you how. So let's go ahead and create this pod by running this command, and then I'm going to describe this pod. And somewhere in here you will see that there is a file system that is mounted using the secret. Remember, we saw that a secret was created when we created this account. So that is actually mounted as a file or a directory inside this pod. Okay, like if you go to this path inside this pod, then you will see that. So let's go ahead and do that actually. So kubectl exec -it test pod, and I want to have bin bash shell. So now let me actually just do ls of this directory, and that will show all these files which contain the token information and certificate information that we need to basically interact with the Kubernetes APIs. So what I'm going to do is I'm going to actually just copy the token inside environment variable from this file. So cat is just a command to actually just print the contents of this file, and then I'm storing all that inside this environment variable, right? So then I'm going to be running this command, which is basically going to pass this token, and then it's going to interact with this Kubernetes cluster using the service name, right? And I expect this to fail because obviously this service account does not have access to this pod actually, or access to any Kubernetes resources. So that's what this is saying. The new SA account does not have access. It's forbidden to access this particular URL, right? So now why do I put HTTP Kubernetes? It's because I have a service called Kubernetes that is created as part of installation again, and that is available for these kinds of pods to use. Actually, it's like any other service, like an application service. Okay, so now what I'm going to do is I'm going to create a role especially for this service account. So I'm going to show you how the role looks. In this role, I am just saying like I want to be able to run these actions or these verbs against this resource. So I'm just want to be able to get, list, and watch pods, right? Now let me go ahead and create the role. So that's done. I want to associate this role with my service account. So this is the service account, and this is the role that I'm actually referencing in this role binding. So we need to create a role binding, right, where we bind a set of accounts with roles, right? So let's go ahead and create this role binding. Okay, so I've created this role binding. Now, so all I want to do is just get into that pod and run the same commands that I ran before. Let's see if we can access the Kubernetes API from this pod, right? So I copied the token into a variable, and I am running a curl command to access that particular path. And obviously this path is still not accessible because the role or the role and the role binding that we created is only to access the pod URL. So the pod URL is a specific URL, and I will show you how it looks. And you can get all that from the Kubernetes documentation. I'll show you where it is. So you see, this is how the pod URL looks. So it's basically all this and followed by the token information, right? And now we are able to get some output out of this curl command, right? So if we want to just grab the pod names from the output, I'm going to use this utility, and now we just parse this JSON, and then we are able to just retrieve just the pod names. And as we saw before, we have a couple of pods which are created by deployment that I did before, and the test pod that I just created. So that actually kind of, it proves that this pod is able to access Kubernetes APIs, right? If we try to access any other resource, it will not work. That's pretty much it. So this is how actually you use service accounts. Now from this pod, you can do node maintenance operations, or you want to do deployments of your application and things like that, as we mentioned before. So what we're going to do is we're going to take an example that is provided in Kubernetes documentation, and using which we're going to understand this horizontal pod autoscaler. Okay, so let me just tell you in plain simple words what it is first. So when you have a deployment or a daemon or a replica set, you can actually increase the number of pods in that deployment or replica set, right? You can increase the number of pods, so you can have one pod or you can have three pods, and you can just increase it manually, like we all know that, right? So what if we can do that automatically? So for that purpose, actually Kubernetes itself provides a method. We can use this horizontal pod autoscaler resource to make that happen. Okay, so if that wasn't making sense, actually just stick with me. I'll probably the example will help out. So in this example, what they are doing is basically they are going to spin up a web server that runs some PHP code, and we're going to actually put a lot of load on that web server, and we are going to make it scale automatically. So the first thing we're going to do is this thing actually. So we're going to check whether your Kubernetes is at least this version, right? So 1.23, right? So we can do that by running a kubectl command, kubectl version. So I actually upgraded my Kubernetes cluster last week to version 1.23, so we're good there. The second thing we need is actually a tool actually called metric server, and if you click here, it takes you to a Git repo, and they tell you like all about it. But it's basically a mechanism to collect metrics about your resources like CPU, memory usage, that kind of thing. So what I did was I just copied this HTTP and I downloaded it using a wget command. So like wget and then that HTTP link. You get this YAML file, and if you go into the YAML file and if you go down to this resource, basically like a deployment of metric server, you have a bunch of arguments, and you need to actually like add this kubelet insecure TLS to actually skip the certificate checks. And of course, if you're doing a production deployment, you want to actually take care of that. But for this particular example, we don't need all the fancy fancy certificates and SSL checks and all that. So I just downloaded this file and I added this thing to that particular metric server resource. Okay, So now I save that, and I'm going to just apply this YAML file to create the metric server uh, tool. So it creates a bunch of things. It creates roles, role bindings, service, and a deployment, and an API service, right? So all these things are created. We don't need to understand what they are, but I'll just show you what they can do actually, right? So back to our horizontal pod autoscaler or autoscaling. So what we are going to do is we're going to take this YAML file. It's a huge YAML file, and we're going to go here and then just create a file called hpa.yaml and then put this YAML code in here. So this one, it just creates a web server. It creates a web server, and it's going to run some resource intensive PHP code in it. Okay, so, and then it's going to create a service called PHP Apache, and then it's going to expose it on the port 80. Okay, and they are providing an image, which is already built by Kubernetes. It's for this documentation purposes. So we're going to just go ahead and apply this YAML file as well. Okay, cool. So now there is a deployment, there's a service, and if you just want to just check the services, you see like a couple of services, right? And then if you want to check deployment, check the Kubernetes deployments on this cluster. So there's a couple of deployments. So I'm just going to delete this deployment just to actually clear up some space in my cluster, because we're going to be creating a few pods, and I don't want any resource conflicts. So then I'm going to delete this. What I can do is I can just delete the pod actually. Okay, cool. So now we cleared some resources. So let's go back, and here so what we're going to do is we're going to run this command to apply the auto scaling thing, right? So it auto scales this deployment that we just created, and we're saying like it's going to be the minimum number of pods going to be 1, the maximum number of pods going to be 10, and the threshold, CPU percentage threshold, is 50. What they mean by that is like if basically the HPA controller will increase and decrease the number of replicas to maintain an average CPU utilization across all pods, 50% actually, right? So this HPA controller is going to maintain the CPU usage at 50%, right? Or below basically. So we're going to run this command. So that's cool. So we have run the auto scale command, and now let's try running this kubectl get hpa and see if so. It's going to take some time to populate. Okay, right now the CPU consumption is only 0%, right? So you can do kubectl get deployment. There's only one pod that is running actually, which is in this deployment. So now what we're going to do is we're going to run this command in a different session in the same cluster, and this command, it basically creates another pod, and it's based on this image, and then inside this image we're running a wget command on this PHP Apache service, this particular service, and we're going to put a lot of load on it actually. That's the point, right? So we're going to put a lot of load on it. Okay, so I'm going to go here and run this command. Okay, so this is cool. The load is, it should be going up. In the meanwhile, what we can do is we can just run this command over here to actually monitor the HPA. All right, you can see that the CPU usage just went up like crazy, 223%. That's like huge. So it's going to keep going up. So what we're going to do is we're going to cancel that command. See, it just keeps going up. Like we don't. So already like the autoscaler has kicked in, and then it's increased the number of replicas to 4. So I'm just going to cancel this command. Just cancel it. And I'm going to run the other command, which is this command right here, to see how many pods we have now. We have 5 pods now. So, and it's going to keep increasing as long as so now this one, we're going to watch the HPA, right? So right now the pod, the average CPU consumption or CPU usage percentage is around 66%, which is still high. My guess is it will go like up to 6 or 7, and then it will stop. Yeah, so it's around 7. We're still doing 58 percentage CPU average across all pods, and it's going to go up until the CPU average CPU usage on each pod comes down actually, right? So this is basically what the horizontal pod autoscaling can do actually. Okay, what I'm going to do is I'm going to just create a pod using my kubectl run command, and the name of the pod is going to be busybox1 based on busybox image. If you're not familiar with this image, it's just a simple image that's based on Alpine Linux, I believe. So we're just going to create this pod, and as soon as the pod gets created, this particular command will run inside the container which is in the pod. Okay, so that's not so important actually, but what is important is basically where this pod is scheduled. What I mean by that is, so if you do a get pods command and a wide output, it shows you where your pod is running. So in my Kubernetes cluster, I have a master node and 2 worker nodes, right? So my pods are usually scheduled on these worker nodes, and there is a reason for that, and we'll come back to that later. But basically this particular pod, when I created it, Kubernetes took a decision to schedule or to place this pod in node 2. Okay, and what if I can actually manage or control which pods can be placed on which nodes? Okay, and one example that I can think of is this, right? So let's say I'm going to say only pods that are based on Nginx web server should be placed on node 1, and pods which are based on the Apache HTTPD web server can be placed on node 2. Okay, so what I've done here is I've basically tainted my nodes. Like I've reconfigured my nodes in a way that that actually controls how the pods are scheduled by Kubernetes, right? So in my taint command, I'm saying, okay, this is the node name and this is the key value pair, right? This is the key and this is the value, and this is the operator, right? Equal to operator, and there is a colon, and this is what is called as taint effect. Okay, and there are 3 possible values for taint effect. One is no schedule, another is no execute, and the other one is prefer no scheduled. Okay, so if you go to Kubernetes documentation, if you look at the taint command in this link over here, you'll basically get all these values and the syntax and whatnot, right? So basically, we'll come back and see what each of these basically means. But for now, the only thing that is important is node 1 is tainted with this key value pair and node 2 is tainted with this key value pair. Okay. Now, if I just randomly create a pod, like let's say busybox2, again based on busybox image and everything else just being the same, and let's look at the pod information, you will see this particular pod busybox2 is in pending status and it's not scheduled anywhere. And the reason for that is we haven't actually specified a toleration configuration for it. If there was another node without any of these taint rules, then this pod might have been placed on that node. But unfortunately, we don't have a free node per se. Okay. So what I'm going to do is I'm going to show you how to actually attach a toleration for a particular pod. Okay. So I have like a YAML file for creating a particular pod called Nginx. Okay. And this pod is based on Nginx image. And here in the pod spec section, I have a tolerations section. And in here, if you pay attention, we have a key called front end and value called Nginx, and then the operator called equal. Okay. So if you recollect, actually when we tainted our node 1, basically we had the same configuration, right? Key is front end, value is Nginx, and then the effect is no schedule. The operator right here is equal to, right? So that's the operator that we have here. So rest is all the same as what you would do normally. So I'm going to create my Nginx pod with this tolerations actually, right? So what I'm going to do is run kubectl create -f nginx, or I can also run apply -f nginx, the YAML file, right? So the pod is being created, and do you have any guesses for where the pod will be created? So since we tainted node 1 with the same key value pair as what we mentioned in this YAML file, I am guessing actually this Nginx pod will be placed on node 1, and that is correct, right? So let me take you into another YAML file called httpd, and it's for creating another pod called httpd, and again based on httpd image and with this toleration configuration and everything being the same except this value. The value is httpd, right? So if you remember, we tainted node 2 with basically this this configuration, right? And I'm saying this pod tolerates this taint configuration. Okay, so let's go out and run the same create command, except this time I want to use the httpd YAML. So we have that, and let's get the pods information, and as you can expect, this particular pod is scheduled on node 2 because this pod tolerates this node, the taints on this node. So that is how you actually control or manage the scheduling of pods. Okay, and busybox2 is still in the pending state, and let's say I want to actually remove the taint on node 2, for example, or node 1, it doesn't matter. So we want to remove taint on a particular node. How can we do that? We can just use the same taint command with this taint configuration, except this time I'm going to put like a minus at the end. So now let's go look at the pod configuration, and you can see that this BusyBox2 pod is now scheduled on node 1 because I have removed all the taints on this particular node. And if you actually pay attention, none of the pods are getting scheduled on node my master node or my control plane node. And the reason for which is, if you describe the master node, and if you grep for taint keyword like this, you will get the taint configuration that is currently applied on that particular node. So when you do a Kubernetes installation, master node is basically configured with this particular taint. So that way, actually, like only the pods which have this toleration is scheduled on the master node. Okay, so similarly you can actually find the taint configuration on other nodes as well. As you know, we just removed the taint on node 1, and we still have this particular taint on node 2. Okay, so let's actually get the pod details again and see how it is going. So let's say on node 1 again, I want to apply the taint, but this time I want to apply the taint with no execute instead of no schedule, right? So I'm applying the taint again on node 1, and let's see what happens to the pods that are running on node 1, right? So you can see that Nginx pod was immediately terminated, right? It was running on node 1, that was immediately terminated, and BusyBox2 is currently in the terminating state. So that's what happens actually. No execute kind of kicks out the pods which are already running on this node, the pods that do not have the same toleration as this. Okay, so we have looked at no schedule and no execute. So no prefer schedule or prefer no schedule basically is another value that we can put in this place right here for taint effect. What this means is basically it will try to not schedule any pods on that particular node, but if there is no other way, it will schedule our pod on that node actually. Okay, so that's called prefer no schedule. So I'm not going to go into that. You can actually take that as homework. So basically you want to learn how to control the placement of your pods, right? So you want to like kind of like define where your pods will be created, which nodes. So if you want to learn how to do that, then basically you want to understand how these methods work. There's also pod affinity and pod anti-affinity, which we're not going to go into. Okay, first thing is actually labels. So you know that you can create labels on your nodes, your Kubernetes nodes. So the second screenshot here shows like the labels of the nodes in my container, and it shows like certain pre-existing labels that came or that were created as part of the installation. Also some labels like location India and location USA and environment, and all these labels which I created. Actually, these are custom labels that I created, and I used a kubectl label command for that. So you can label your nodes. So the first method is node selector, so which is a very simple method. So basically you have in your pod YAML file or whatever resource you're working with, you can actually add a node selector section where you put the label, which is basically a condition that that is checked actually by the scheduler. For example, if you have a bunch of nodes, only the nodes which satisfy this condition, this location equals USA, will be eligible, and scheduler will place your pods in one of those nodes actually. So that's basically the way it works. So you can have multiple labels under node selector. You cannot have multiple labels with the same key and different values, so that will not work properly. So that's the one thing that you need to remember, but you can have multiple labels. Here's a node affinity and anti-affinity. So basically similar to node selector section, you have the affinity section under which you have the node affinity, and you have this long phrase which is required during scheduling, ignored during execution. We'll come back to that. Basically you have the same condition expressed in a different way, and this is sort of like a better or a clearer way to actually define your condition, where it clearly says, I want like a node with this key and this particular value, and this is the in operator. And you have a few more operators, operator options like in, exist, does not exist, greater than, less than, not in, all these options actually. So you have more options when it comes to node affinity. So if you're using node anti-affinity, then you basically use not in and does not exist option. So you can use those two operators in case of node anti-affinity. So here is basically a table that shows you can have the required phrase or the preferred phrase, and one is actually a hard rule, meaning like the conditions under the required phrase is actually a mandatory condition, and the conditions under the preferred phrase is actually a soft condition. Or like basically Kubernetes scheduler will try to find a node based on the soft rules. If it doesn't find a node, it will pick a node on its own actually, randomly. So here's an example where both the required and preferred conditions are used. Required is again a mandatory condition. Preferred is where you have a bunch of conditions actually, and then you have the weight associated with each condition actually, right? So it will go through each node in your cluster, and it will the Kubernetes scheduler will start assigning a total weight to your nodes, and the node with the highest weight will be selected for placing your pod while pod is being created actually, right? So that's basically the point. Finally, you have the node name. Node name is basically a straightforward approach where you put the node name next to the node name keyword, and but this is not really useful in a cloud environment where the node names are unpredictable, and so this is probably going to be useful in your lab environments, but this is another way you can accomplish the same outcome. And finally, like I just wanted to list out the use cases where you might need to use this. Uh, so quickly, I'm going to read through. I'm not going to go into details of this. So basically, high availability, node maintenance operations, node isolation or pod isolation, and putting your pods based in a certain set of nodes based on the security groups, caching requirements, etc. So these are various options that are various use cases where you might need to assign pods in a certain manner. In this video, we're going to be talking about Kubernetes services. Especially, I will be highlighting the difference between these things actually: port, target port, and node port. And don't worry if you don't understand what they are. I'll show you a demo which will make it very clear. So I want you to imagine a scenario. Basically, in this scenario, let's say you are a software engineer working for a huge company, a big company, which implements these DevOps technologies like Docker, Kubernetes, Jenkins, CI/CD pipelines, etc., etc. So basically the DevOps ecosystem. And you're working for a team which is developing a web application or a certain REST API, right? They're done with coding, and you created a build process which basically creates a Docker image, right? That's the output of this build process. Now, your task is to deploy this Docker image in a Kubernetes cluster, right? So I hope you're with me so far. Very simple. You need to deploy a Docker image in a Kubernetes cluster. So let's actually start with this diagram. So we're going to create a deployment in Kubernetes. Basically, a deployment is a kind of resource in Kubernetes, and let's see how how that looks actually, right? So let me grab this YAML file. In fact, I've copied this YAML file to my Kubernetes cluster. So I'm logged into my master node in Kubernetes cluster. Okay, so and it looks like this. So this is the deployment API. So you don't have to worry much about it, at least as far as this video is concerned. And this is what we are creating is a deployment. And we've got some labels and the name of the deployment. And then this is the spec of the deployment itself. So this deployment has only one replica, and it's got a selector section for identifying the pods which are related to this deployment. Okay, and this is the template of the pod that will be created, and specifically this is the spec of the pod. What that means is the pod that is related to these deployments is basically using this image, and this is the Docker image that I was talking about. Let's pretend that this is your Docker image and it uses a specific version. Okay, so in short, we're going to deploy your application, and the application is going to be running inside a pod, and the pod is basically based on this image. I hope that was clear. Okay, so let me create this deployment. It's pretty straightforward, and let's make sure the deployment got created. Okay, so we have created this deployment, and let's see what pods are running inside. kubectl get pods. So we have this pod running inside, and let's find the IP of this pod, and this is it. So I'm going to use the curl command and hit this IP, right? So what we are getting back is the default web page from the Nginx deployment inside the pod, right? So this is, you can see it says welcome to Nginx. If you see this page, the Nginx web server is running or successfully installed, right? Blah blah blah. So where we have successfully deployed your application, right? So now let's say like we give this IP out to some client or another pod. Actually, if I go back to this diagram over here, this is what we've done. A deployment which has pods, and IP of the pod looks like this, and the target port is basically where the application is running. And if you're not sure about that, so let me do a curl IP of the pod, and then if I do provide the port also, the default port of Nginx is 80, right? We're still getting the same web page back. So that is the target port, and please remember that. Okay, so now we're going to create, before creating the service, the reason why we are creating the service is this. So let's say we give this IP to a pod or some other application, right? So they are going to reach our web server through this IP, actually, this particular IP right here. Now, let's say like we want to do another deployment, and this time we are going to deploy a different version of the application. So I'm going to come here and then I'm going to say, okay, deploy the latest version of my Docker image, my application. Come out after saving that YAML file, and let's apply this one. So basically we have applied this new deployment changes. Okay, now if I go back to my curl command and if I run it, it will not run. You see, this is hanging actually, and that's because if I look at the IP of the pod, it looks like this, right? It has changed from what it was before, right? So, and that's because when we do a new deployment, your pods will be recreated, and every time there will be new IPs for those new pods actually. So you cannot actually give the pod IPs to your your peers, the other services which want to reach your application, right? Like to this guy you cannot give the pod IP. So what can we do actually? We have to create a service. So how can we create a service? So that we can do by using kubectl expose service, and actually we want to expose a pod, or more specifically a deployment, and the name of the deployment is nginx TEP, and the target port is basically the port on which your application is running in the pod over here, that is 80, and the port on which this application will run is 80, and that's it actually. So when we create a service like this, and let's actually look at the service, that service is going to be of type cluster IP, and it's got a cluster IP which is a stable IP, and it will not change no matter how many deployments you do. First of all, let's make sure actually this IP or this IP is usable to reach our web server behind the scenes, right? So I'm going to be using the port 80 as well, and that works, right? We are able to reach this nginx web page through the service IP or the cluster IP. Now let's go ahead and do another deployment and come out here. Instead of latest, I want to do, let's say, 1.21, some other version. Okay, now all I'm going to do is basically apply this new deployment YAML file, this modified YAML file, and we have done a new deployment. And what happens to our service? It does nothing actually. It does not change, because you see this IP 181.240 is the same as this IP. So this IP is stable. So if you provide this IP to another service which is running in the same cluster, they will be able to reach our application, no problem. And no matter how many deployments you do, this IP doesn't change. Okay, so I hope that was clear. Okay, now what is node port? So we have seen what is port. The port is the port on which our service runs, and the target port, which is the port on which our application runs inside the pod. And what is node port? So for that, I'm going to actually like delete this service that we just created, and I'm going to go back to this expose command to create a new type of service, and this time I want to create a node port type service. Let's come back to this diagram. So this one we already see, right? We deployed, we created a service, we gave the IP to another pod which is running in the same cluster, they're able to reach the pod or the deployment or the application through this service IP, this table IP. Now here we are. So we're going to create another service, but this time we're going to reach the application, the web server, from outside. From outside, as in from outside the cluster, externally, right? And let's say I'm creating a YAML file out of this. Let me go into the YAML file. So we need to provide like a node port, which is the port through which we will be able to access this application, right? So let's actually provide another value here called node port, and it has to be about 30,000. There is a range, a certain range that you should use. I think it's 30,000 through 32,000 or something like that. I'll provide that in the description. And then we have a target port as well. Target port, and that is 80. Let's come back here. All right, so let's look at this service. So this is a node port type service, and it's got an IP, and inside the cluster it's going to use, the service is going to use this 80 port, and it's going to use this 30,000 port as well. Now what is this 30,000 port? So let's go ahead and go to my AWS console. I'll grab one of the 3 IPs, right? This is my master node, and I have 2 worker nodes. I'm going to grab the IP of one of these worker nodes. It doesn't matter, we can pick any one of the 3, and I'm going to just open another tab and put the IP there and colon 30,000. Then we should be able to reach the application which is running inside the cluster. You've seen what a cluster IP is, and you've seen what a node port is actually, right? So let's go back to the diagram over here. Now we can basically reach your application through this path. We go through the node port, and then through the service into the application that is running in this deployment. Okay, and we can also go through another node, basically any node in the cluster.